So the first of the methods we'll look at then is the classical F test. So this is one of the, sort of classical frequentist statistical tests. The F test crops up all over the place. It appears, for example, you might have come across it in analysis of variance. If you've ever had to do an analysis of variance test, there are other situations where it arises. And in general, what it does is to compare the variances of two distributions. And more specifically, it tests the null hypothesis that the variances of two sets of samples are the same. And we can use that in model selection by applying that test to the residual errors that we get from fitting those two models to a set of data. And so it sort of uses the idea of the law of parsimony, Occam's razor, by saying that if we have one simple model and then a more complex model, and the variance of the residuals from those two models is the same, then we might as well stick with the simpler model rather than the more complex one. We've got no justification for using the more complex one if the variance of the residuals are the same from both. We apply law of parsimony and stick with the simpler one. So that's broadly the idea behind it. So strictly, you can only use it for sets of nested models. What do I mean by nested models? So those are sets of models where the more complex one is a direct extension of the simpler one. So specifically, if the simple model M1 has parameters x1 up to n1, the complex model also has that exact same set of parameters, but it has some additional ones as well. And when that's the case, then we perform this test on the null hypothesis that the variances of the residuals of these two models are the same. And if we cannot reject that null hypothesis that the two are the same, then we accept the simple model. If we can reject it, we accept the more complex model. And as with most of these kind of classical frequentist statistical tests, there's a fairly sort of standard recipe to go through for applying the test. This is it here. You can look it up. Actually, there's a nice description of this and other related tests in this Armitage and Berry book. There are loads of other books on these statistical tests. I picked through this in the demonstration, so I'm not going to go through it in great detail here, but just very briefly. So the way we do it then is to compute this F statistic here. Let's just quickly look at what it is. So we fit each of our models to our data to find the best fit parameters, x tilde. Then we can, having done that, we can predict the values of our measurements at each, corresponding to each measurement that we've made for those best fit parameters. That's these M's here. And then compute this number here, the variance of the model. And so that's just the values of those predicted measurements minus their mean, sum of squares of those. So that gives us the variance of the model itself. We take the difference of those and divide by the mean squared error of the more complex model to the set of measurements. A couple of weightings in there. The K is just the number of measurements, and the N's are the numbers of parameters of the more complex and the simple model. So anyway, it gives us this, we compute this statistic F, and then under the null hypothesis, that statistic F, so if the variances are genuinely the same, then F follows an F distribution. An F distribution is a probability density function with that looks a bit like this picture I've just drawn. So it's always positive and slightly skewed above 0. It's actually a two-parameter family of distribution. It's got these two parameters to it, which are called degrees of freedom, that can change the sort of position of the peak of the distribution and how skewed it is away from 0. So, okay, so we're saying that this statistic F then follows this distribution under the null hypothesis. That means that if we were to repeat this experiment time and time again, reacquire our measurements fit the two models, compute the F statistic, we would get a range of values that all lie in the action part of this distribution. If we compute a histogram of them, it would approximate this distribution. And so that in turn means that if we compute a particular F, when we evaluate our F for our one set of data, and we find that it's way out here in the wilderness of this F distribution that it should lie in if the null distribution is true, that gives us the evidence to reject the null hypothesis and accept the more complex model. Okay, so yeah, simple and classic kind of statistical test that allows us to choose between two nested candidate models by comparing the variances of their. Yeah, just to wrap up then on the F test. So very useful and effective when it's appropriate, but does require that we have nested models, and is not appropriate in situations where we don't. For example, if we wanted to compare the ball and stick model to the diffusion tensor, we can't do it. Also makes the assumption of Gaussian noise, and should bear that in mind if you're making an application of the F test. And one other sort of limitation of the F test compared to some of the other techniques that we'll talk about in a moment is that it just makes this hard decision. It says, it makes a simple binary choice between the simpler model and the more complex one, whereas, as we'll see shortly, some of the other techniques can give a relative likelihood of two different models, which enables us to do some nice things like combine information from different models to make sort of consensus estimates of parameters or predictions. Okay, but